Hi guys, good evening. Hello bachcha log, how are you guys? Let me know in the chat box how are you feeling today. My name is Shubhang Garodia, chemistry master teacher at Vedantu, and we are going to conduct a brilliant session, a super awesome session on quick revision of physical chemistry. So I hope you all are feeling great, you all are feeling awesome, you all are pumped up, charged up for the session. Let me know in the chat box with some yo. Come on guys. Let's have some noise on the chat box. I am visible, audible clearly, right? You can see me, view me clearly, all good, all okay? Brilliant. Let's start. So guys, what we are going to do is in this session, we are going to concentrate on thermodynamics and we are going to concentrate on chemical kinetics. Hi Harsh, hi Subhadra, how are you guys? All good, all okay? I hope you have been watching the other sessions that I have uploaded earlier. We have talked a lot about reaction mechanism, we talked a lot about mole concept. So let's start quickly, and the first thing that we are going to discuss in today's session is thermodynamics. So the flow of the session will be, guys, what I'm going to do is I'll show you a slide, I'll discuss few formulae, few concepts that are given on slide, and we'll talk about the important things that need to be kept in mind while using the formulae. Okay, let's begin. So thermodynamics is a very big chapter. I have tried to cover as many formulae as I can. Let's start off with our very first thing, that's the first law of thermodynamics. We know that the first law of thermodynamics states du equal to dq plus dw. Now this is your which form? Differential form or integral form? This is your differential form of first law of equation, first law of thermodynamics. When you integrate it, it converts to this. Mind you, dq ka integration is not delta q, dw ka integration is not delta w. That's wrong. Delta is used for state functions, not path functions. We know that. Work and heat are path functions. So dq means small heat exchange, dw means small work done, and when we integrate it simply comes to q and w. Now one thing it is very important to note here. What do you mean by this q? Is it heat absorbed or is it heat emitted? What do you think what it is? Let me know in the chat box. Is this q heat absorbed by the system or heat emitted by the system? Is this W work done on the system or work done by the system? Isn't it important? Don't you think so? That if we know what is first law, we should know that here Q and W signifies what? So here Q and W signifies heat input, heat absorbed by the system, and here W signifies work done on the system. Now here itself I'm going to talk about the sign convention also, guys. We say that when the system is emitting heat, when it is liberating heat, it is negative and we call it exothermic. When it is absorbing heat, that is heat is incident on the system, then we say it is endothermic and positive. Similarly, work done. See, chemistry mein we are considering the system, we are observing the system, what is happening to the system because of the changes that we are making. So W is also positive when work is done on the system. When work is done by the system, work done is negative. Anything that goes to the system is positive, taken out from the system negative. Very simple, very easy to remember. Now next part. Another very important point while problem solving, especially when it comes to cyclic questions or cyclic processes, is delta U equal to 0. Now mind you, Q is a path function, W is a path function, but its sum comes out as what? Its sum comes out as a state function. Why does this happen? This isn't supposed to happen. Two path functions ka sum coming out as a state function. The answer essentially comes from this. We will not go into the derivation right now, but the answer comes from this, that first law is essentially this, the differential form. Now, while solving cyclic process ke questions, the change in internal energy when you complete a cycle, when you come back to the same point, is 0. That means, it means sum of work done plus sum of heat exchanged is equal to 0. So this is a very, very important point when we talk about cyclic processes, cyclic process पे solve होने वाले questions which we end up missing. चलो, next point. Now, the next part that is very important after first law, we'll talk more about first law, about work done, etc. But let me first talk about enthalpy. Internal energy is the total sum of energies that are needed to keep the system in place, to keep the system intact. It is a sum of kinetic energy of particles, sum of potential energy of particles. That is the energy the system needs to possess to keep the system intact, to keep it in place. But that's not enough to define the total energy, and therefore we end up adding a pressure volume term. So enthalpy, which is the total energy content of the system, is equal to internal energy plus the energy possessed by the system due to pressure volume, due to its expansion compression capabilities. Now, this is written in an absolute format, but we know that absolute measurement of H is not possible, just like absolute measurement of U is not possible. Meaning, we can always find delta H, we can always find delta U, change in enthalpy, change in internal energy, but we can never find absolute value of H and U. So this formula is practically useless. We start off by differentiating the whole thing. So we get this. And then guys, based on the condition given to us, the formula changes. I'll write the formula again. The formula was dH equal to dQ plus d of PV. And as you can see, for an isobaric process, that is pressure constant, this P comes out. So integrating gives you this value. Now what is this P? Is this P internal? Is this P external? Pressure is kept constant. Whose pressure is kept constant? System ka pressure is kept constant or the external pressure is kept constant? What is this P? Any idea? Can somebody tell me on the chat box? When we talk about this equation for an isobaric change, we are saying P is kept constant. So what is this P? Is it system ka P or is it external P? Pressure of the system or external pressure? This here, guys, is pressure of your system. We are not changing internal pressure at all. That is why we are able to take it out of the differential. Similarly, when we talk about isochoric process, volume comes out of the differential. If pressure and volume both are changing, then we prefer using P2V2 minus P1V1. I hope this much is clear to everybody, guys. We have talked about first law ka basic formula, delta U equal to Q plus W. We have talked about enthalpy ka basic formula, that's del H equal to del U plus delta of PV. This on integration gives us del H equal to del U plus delta of PV. Delta of PV we can write based on the process given to us. Now, using first law and enthalpy, first law states del U equal to Q plus W. If we talk about an isochoric process, that is in which volume is kept constant, so we know that work done will be 0. Why? Because work done ka basic formula is minus P external into dV. So if it's an isochoric process, dV is 0, so work done is 0. That means delta U becomes equal to Q. We just write it as QV to show the heat exchange is for a isochoric process. If we perform enough mathematics, we can prove that QP is also equal to del H. Now, this formula for ideal gases can be extended to NCV delta T, NCP delta T. Can I use this formula always? Can I use this formula always? QV equal to del U equal to NCV delta T? No. This entire thing, if you are talking about, you cannot use always. You can only use when you have isochoric process. But if we talk about just this part, del U equal to NCV delta T, del H equal to NCP delta T, is this valid always irrespective of the process? Yes. Del U equal to NCV delta T and del H equal to NCP delta T is valid always, guys, no matter what process it is. One simple reason that we can give is del U is a state function, del H is a state function. So it does not depend on what the pathway is as long as T1 and T2 are kept same. Is this much clear? Is it understood? These are some fine points you should keep in mind while solving questions, and these are the points where you actually make up mistakes in complicated ones. So be careful, guys. Be careful. Chale, shall we go ahead? Awesome. So this was all about isochoric process. What do you mean by enthalpy? What do you mean by internal energy? What do you mean by work done? And what do we mean by first law of thermodynamics? Now let's apply first law of thermodynamics on various processes that we know of. This chart appears overwhelming. This chart appears disturbing in nature, but trust me, you know majority of the things already. When we talk about isothermal, that means temperature is kept constant. So del U and del H, whose formula was NCV delta T and NCP delta T, they are by default 0. Del U and del H, because delta T is 0, they are automatically 0. Right? Now, work done ka expression, which we start from dW equal to minus PdV, and we use isothermal conditions, we derive, we remember the formula, minus RT ln V2 by V1. Please don't make a mistake when you convert the volume to pressure. V2 by V1 will convert into P1 by P2. When you change the volume to pressure, it gets inverted. Why? Because PV equal to nRT, pressure and volume are inversely proportional to each other. Okay? Work done wale formula mein there, for a reversible isothermal process, there are no catches. It's a direct straightforward formula. Now, the moment we talk about irreversible isothermal, it's isothermal still, temperature is constant still, it's irreversible. When it's irreversible, we cannot use this differential equation to integrate. When it's irreversible, we always land up using the formula that, work done equal to minus P external into delta V. Reversible के केस में we can integrate, irreversible में we can never integrate. So this is the formula that we'll use. So minus P external into delta V. Irreversible isothermal, if you want to change P and V into temperature, you can. You will get this equation. Something weird happened. There are three pressure terms. There's P external and you can see P1 and P2. Absolutely correct. This is one of the most confusing questions that get asked in the exam. They ask us work calculations, they ask us for an irreversible isothermal process, and we get stuck in the problem. Why do we get stuck? We arrive at this step, then we know that we have to use PV equal to nRT here. We don't understand what to do of this P1 and P2 and this P external. Question may we never have three pressure values, right? We'll have initial pressure value and we'll have external pressure value. That's it. So what to do of this P1, P2 then? Let me help you out. Irreversible ke case mein P external is kept constant. Yes or no? In the case of irreversible process, P external is constant. So if I'm expanding, my P external is the initial pressure. P external is the final pressure. If I'm compressing, P external is again the final pressure, because I have to reach to the final pressure value, right? And I have to stop there. So P external is always equal to P2, whether you are expanding, whether you are contracting. So although we have written three separate terms, but P external here is equal to the is equal to the final pressure here. Clear? Moving ahead, because it was isothermal and these are state functions, irrespective whether they are reversible or irreversible, the change will always be 0. Next two are pretty straightforward. When we talk about isobaric reversible process and isochoric reversible process, direct formula application gives us these results. I'll leave this slide for 30 seconds for you to analyze, then we'll move ahead. In case you have any doubts, in case you're stuck anywhere, please do ask, guys. Please do ask. Quick. Chat box is open for discussion. Hi Vishal. Hi Charan. Hi Sanjeev. I hope things are clear. There are graphs given here also, but they are not of too much use, so I'm not discussing them right now. Awesome. Chalo, let's move ahead from this slide now. So this was about work done ke some formulae. Let's continue work done ke formulae. This is one, as I told you, irreversible isothermal ke questions get asked a lot in the exam, right? Similarly, adiabatic process ke, just a second. Similarly, adiabatic processes ke questions also appear a lot in exam. Whether it is adiabatic reversible, whether it is adiabatic irreversible, whether it is polytropic, which is similar to adiabatic, not exactly adiabatic. So let's go through the formulae properly. Whenever we talk about adiabatic process, that means heat exchange is 0. Heat exchange 0 hone se Q is equal to 0. Even in irreversible adiabatic, heat exchange is always 0. So first law के हिसाब से W becomes equal to delta U, and delta U was a state function, right? Delta U was a state function. Therefore, our delta U का formula does not change. Whether it is irreversible adiabatic, whether it is reversible adiabatic, the formula for delta U and delta H remains the same. ठीक है? Now, since Q was 0, first law tells us W equal to delta U. So if you know delta U, W, so directly we know. Simple. So reversible adiabatic is a simple case to deal with. The moment we talk about irreversible adiabatic, this is also simple. Why is it simple? Q is 0 and delta U ka formula is fixed, NCV delta T. So work done formula also comes out to be the same. Now, one very important thing that you should remember is we can never connect 2 points via reversible as well as irreversible adiabatic process. We can never connect 2 points via reversible as well as irreversible adiabatic process. Okay? What am I talking about? Let me show you on a diagram. If I can manage one, yeah. Suppose these are 2 points. I want to relate them by isothermal process, reversible. This is it. This is how isothermal reversible will be. Suppose I want to relate them by irreversible process, isothermal expansion, let's say. So this would be, I can break this down into multiple steps. That means we can connect 2 points by reversible isothermal as well as irreversible isothermal. I am saying the same thing cannot be done when it is adiabatic. We cannot connect the 2 points with reversible as well as irreversible adiabatic process. It's a very important thing to remember. Okay, guys, now coming to polytropic. What is polytropic process? In terms of formulae, you replace gamma by N. In terms of formulae, you replace gamma with N. N is a number here which is not equal to gamma, which is not equal to your adiabatic gas constant. Okay? But if we talk about theory, guys, it's completely different. In adiabatic processes, we know heat exchange is 0. Polytropic mein that is not the case. Polytropic mein it all depends on what is the value for N. Okay, so in case of polytropic process, please remember the formula properly and these values that will help you move ahead. Even if you remember this properly, it's more than enough. Now, Special cases here get asked based on these two slides. What special cases? Expansion in vacuum. Expansion in vacuum is very simple case. Why should I study as a special one? Expansion in vacuum means P external 0, yes or no? If P external is 0, work done is surely 0. Because work done formula has minus P external in it. Right? So if I'm expanding in vacuum, P external is 0, work done is surely 0. Now, expansion is what that the question needs to tell us, whether isothermal, whether adiabatic. Based on that, delta U or Q will also become 0. So special cases of these two slides are very easy to deal with. Please don't put an effort to mug them up separately. There's already a lot of things to remember. Cool? Okay. So till now we have covered first law. We have covered some basic formula of first law. There is a lot more that you need to study in first law when it comes to thermodynamics and JEE Advanced. You need to be able to compare reversible, irreversible expansion work. You need to be able to compare work done in adiabatic and isothermal when the process is reversible in nature. So all that comparisons also get asked in exam. These were some basics. Let's go ahead. Now, we get stuck in these questions a lot in the exam. We have crazy level pe mugged up that delta H equal to NCP delta T, delta U equal to NCV delta T. We have mugged up these formulae like crazy, and wherever they ask change in enthalpy, you try to use these. It's not correct to use these whenever they ask you change in enthalpy. You can use these only for a process. If it's a reaction or if it's a phase transition, which is essentially a reaction, we don't use these formulae directly. For example, guys, if a solid is converting to liquid, surely the internal energy content is different, na? Solids have lot more attractions, liquid have lesser attractions. So surely the internal energy is changing when liquid is in equilibrium with solid, yeah, when they're interconverting into each other. That is what we are covering right now. The phase change transition formulae for enthalpy. So if we talk about vaporization, we end up with this formula. Where did we get this? Del H was equal to del U plus delta PV. We changed this thing. What is the temperature here? The temperature is the temperature at which vaporization is taking place. The question remains still. How do you find del H vaporization? Del H vaporization is found by two ways. One is we can find this by T delta S of vaporization into T. One is this method. And the other method is del H vaporization, H of vapor minus H of liquid. These are the two ways by which we theoretically determine del H. If you want to relate del H and del U, this is the answer. Now, when we talk about vaporization, when we talk about sublimation, the product is a gas, right? So on the gas product, we can apply PV equal to nRT. And that's the reason why in vaporization and sublimation, we see this RT ka factor coming. I repeat, during vaporization and sublimation, one of the product formed is a gas. And therefore, we see vaporization and sublimation mein delta PV converting into RT. Okay. But now, when we talk about fusion, when we talk about melting, because one side is liquid, other side is solid, both of them are incompressible in nature. Both of them ke case mein, the change in density when they are melting, when they are melting or condensing is not very different at equilibrium. So the PV term does not come into the picture. Del H fusion is equal to del U fusion. Del H melting is equal to del U melting. For solid liquid phase transitions, pressure volume terms contribution is 0. Chalo. Now, why am I talking about this heating curve? This is such a simple thing. We need to understand two things in phase transition. Phase transitions take place at constant pressure. Whenever we are studying any reaction, not just phase transition, we always try to keep the pressure as constant. And when the phase transition is taking place, sorry, if you see here, where solid is in equilibrium with liquid, where solid is converting to liquid, there you see there is no temperature change. What does this imply? Theoretically, this point should be very clear to us. When we talk about heating a solid, unless all the solid is melted, the temperature does not rise. Whatever heat we are giving is going to melt the solid, is going to break the intermolecular force of attraction in solid. Only and only when all the intermolecular forces of attraction of solid are broken, all the solid system is converted to liquid. After that we see, after that the liquid ka temperature starts rising. Simple, isn't it? What if I change the x and y axis? What if I tell you now I'm plotting temperature versus Q, not Q versus temperature? How will it look like? If I talk about plotting temperature versus heat input. So when it is a solid, I am giving heat, temperature is rising. Now when it is interconverting into liquid, when it is equilibrating with liquid, I am still giving heat, but the temperature is not rising. All of the liquid has melted away. Now the temperature will rise. Do you understand how flipping the axis is changing the melting curve? Depending on the y and x axis, we define our melting curve. So this is a very, very small question, but can definitely come in exam. The melting curve characteristics, y versus x mate is different, x versus y mate is different. So if a general question is asked in exam, guys, a horizontal line is obtained in the melting curve. Is that a right statement? A horizontal line is obtained in the melting curve. Is a general statement like this correct? No, general statement like this is not correct. It all depends on how we have defined the y and x axis. As you can see in this case, it's a vertical line, not a horizontal line. Is this much clear? Are you with me, guys? We are talking about thermodynamics. We are revising formula of thermodynamics. We have reached till the end of first law now. We have covered enthalpy. We have covered work done. Let's move ahead. What do you think comes next? What do you think comes next? What comes next is the second law of thermodynamics. Second law of thermodynamics defines entropy for us, right? Second law of thermodynamics tells us that not all reactions can proceed in all directions. Second law of thermodynamics tells us spontaneity ka meaning, it defines the term spontaneous reactions or spontaneous process for us. We say बहुत सारे ways में we can write second law. One way or the most तो नहीं, one of the more scientific ways to talk about second law is with respect to entropy. For every reaction that happens in the universe, the entropy of universe either increases or remains constant. Second law pe lot of theoretical questions can be asked, guys. There are a lot of variations of second law. One of the variation is for every real process that occurs in the universe, what happens? Entropy of the universe either increases or remains constant. If it is a spontaneous process, if it is occurring on its own, then definitely the change in entropy of the universe is positive in nature. It is not equal to 0. When does this come out to be 0? Anybody? When is the change in universe, change of entropy of universe 0? For reversible reactions. For irreversible reactions, that are the reactions that take place in real world, the reactions which are spontaneous gives us change in entropy as positive of the universe. This is not a good way to talk about reactions. Trying to observe the change in entropy of system as well as surrounding for every process, for every reaction is not easy, is not possible. So later we see that del S universe converts to del G system. Yaad hai? Later, the spontaneity formula converts to del G system being negative and not del S universe being positive. Chalo, let's take this entropy discussion a bit ahead. So, when you define entropy, when you define Carnot engine or a Carnot cycle, from there we end up with this formula. By defining efficiency, by defining Carnot cycle, we land up with this formula that ds system equal to dq reversible by T. That means change in entropy of a system depends upon the heat transfer and the temperature at which the heat transfer takes place. Now, we generally don't use this formula directly. What we use is interpretations of this formula. For example, du equal to dw plus dq, first law. So dq can be substituted as du minus dw. So all such variations of this formula get used up. Rarely we use this formula directly. So let's study one such variation. The very first variation is when we talk about an ideal gas. When you integrate this equation using this formula, for an ideal gas, we get this big formula with us. What is this formula? Very easy to remember. NCV ln T2 by T1 plus NR ln V2 by V1. If you are taking volume here, you will get CV here. NCV ln T2 by T1 plus NR ln V2 by V1. You can use this formula to find entropy change of a system during any reversible or irreversible process. Generally, we use it for reversible. You can very well use it for irreversible because this is again a state function. I hope application of this formula is clear, guys. How will you apply this formula? Isochoric matlab volume change nahi hai. There's no volume change. Second term 0. Isothermal, no temperature change. First term 0. And we can always write this in terms of pressure. NCP ln T2 by T1 plus NR ln P1 by P2. So if it's an isobaric process, then this term becomes 0. Sorry, not this. This term becomes 0 for an isobaric process. So there are many ways by which you can use this formula depending on the process given. Are you guys understanding? All good? Entropy pe questions asked are rare in exam, but when they get asked at a very complicated level. In general, multiple correct type questions mein we see theory based MCQ question, theory based questions on entropy. Formula based are simple. For ideal gas we use this formula, and otherwise we try to use variation of this. What do you mean by variation of this? So during a process, not a reaction, we use NCV ln T2 by T1 plus NR ln V2 by V1. But what if it's a reaction? What if it's a reaction? Whenever there is a reaction taking place, we simply use del S equal to del H of the reaction upon T. How? ds was equal to dq reversible by T. dq means heat exchanged. In a reaction, del H is equal to the heat exchanged. Why? Can I say for all reactions QP equal to del H? Can I say for all reaction QP equal to Q equal to del H? Yes, we can. Remember, we study all reactions at constant pressure and temperature. If we study all reactions at constant pressure and temperature, QP ही तो आएगा. QP का formula will come as del H. Therefore, we are using this formula everywhere when we talk about a reaction happening. Sublimation, del H sublimation. Vaporization, del H vaporization. Fusion, del H fusion. Is this much understood? Del S for system. These are system calculations. For phase transitions, we get very simple formula. Direct plug-in value, get the answer. Now, from here also you can understand, guys, when we convert gas to when we convert liquid to gas, when we vaporize a system, entropy change should be positive or negative? Observe this formula. delta H vaporization value. When we convert a system from liquid to gas, when we vaporize a liquid, we have to provide enthalpy of vaporization. We have to heat the liquid. That means del H is a positive term. So del S is also a positive term. When you convert liquid to gas, the randomness increases, the force of attractions decreases, and so we say the entropy change is positive. Chalo, आगे बढ़ते हैं. Now, that was one way to find entropy change of a reaction, which we wrote as del HR by T. The other way is your standard way, कि change in anything is equal to products minus reactant. So entropy reactant minus entropy of product minus the entropy of reactant. We generally don't use this formula because just like absolute enthalpy, absolute internal energy, absolute entropy value cannot be measured. Now, important thing from JEE Advanced purpose is del S surrounding calculations. Del S surrounding calculations are very important. They trip you in the exam based on this itself. Examiner very well knows that del S system you can calculate easily. But del S surrounding is where you get stuck. If we talk about no heat loss, if we say that heat loss is equal to 0, so Q system can be said as minus Q surrounding. Heat gained by the system is heat lost by the surrounding. If there is no heat losses due to vibration, due to sound, we can say that this is valid. So that's all we are doing. Please check. That's all we did. Del S surrounding ka formula would basically be equal to Q for surrounding upon T. And Q for surrounding we are writing as minus Q system. Thermo mein na, not all formulae should be mugged up. A lot many formulae we should keep developing as we are solving questions or when we are in the exam. This is one of that situation. Clear guys? Got it? Anything you would like to ask, anything you would like to discuss? You have 1 minute before we start off further discussions. Before we start off further discussions, I'm opening up the floor for doubts. You have half a minute. Quick, bacha log ask doubts. If not doubts, you can tell me how do you feel about thermodynamics? How do you feel about JEE Advanced coming up soon? Vishal, Yuvresh, Yashwant. How do you feel about this chapter? How do you feel about JEE Advanced coming up soon? Scared, excited, prepared, nervous? Mixed feeling. That is a good situation, you know, mixed feeling, because if you tell me you're not at all scared, that means you're not at all prepared. Right? So that's a good feeling that you have mixed energies, mixed vibes coming. So you'll keep studying also and you'll be scared also. That's a good thing. Yes, Manjit, absolutely. We teachers here also dhak dhak ho raha hai as exams are coming close. Let's start. This I've already discussed with you on the previous slides. This is also where SCQ type question comes a lot in exam. They ask us entropy change is positive or negative. 15 minutes, I think. 1 hour class. So they ask us positive or negative change is happening in the given reaction. We need to understand that lesser denser phase has more entropy. See guys, entropy ka logic of randomness na in our heads is wrong. Entropy का मतलब randomness से है in the sense more options for the molecule to move. Do you know something called degree of freedom? A molecule can move in the XYZ axis. It can vibrate along various axes. So more such options the molecule or atoms have, more is the entropy. That is what the logic of randomness is. So we say gas particles are lesser attracted to each other. They can move about more freely. So more entropy of gas in comparison to liquid. we know that in a reaction, if I have solid CaCO3, if I have solid in the reactant forming CaO solid plus CO2 gas. So here, since we have gas product in the, so ऐसे बोल लो इसको guys, del S of the reaction would be entropy of product का sum minus entropy of reactant का sum, and this value will be very very high. Why? Because product में there is a gas molecule present. If product में there was no gas molecule present, if there were only liquids and solids in reactant and product, then it is very difficult to talk about entropy. Entropy change can only be predicted when you have gas on one side at least. Is this point clear? The next point is, suppose you have H2 goes to 2H. What do you think? Entropy change is positive or negative? Come on guys. What do you think? Entropy change positive, negative in this case? Entropy change here is positive. Entropy change here is positive. Although a single atom in comparison to a single molecule, if I do, I will get different answers. Here we are not comparing single atom and single molecule. One molecule is giving multiple atoms. So overall entropy change is positive. If we would have compared H2 with a single H atom, then we'll get negative. But when you're comparing H2 with all its constituent atoms, it's always a positive value. Okay? Now, tell me one thing guys. If I have N-hexane converting to cyclohexane, if I have normal hexane, linear hexane converting to cyclohexane, what do you think about change in entropy? Positive, negative, zero of the system, of course. If you have linear hexane, N-hexane, 1, 2, 3, 4, 5, 6, converting to cyclohexane, entropy change will be negative in this. Why will entropy change be negative? Because a linear system, see, one second. If we talk about a linear system is free to move around, right? It can interact with other molecules, other atoms very easily. But if we talk about a cyclic system is very difficult to move around. There are a lot of restrictions in the cyclic system. And so we are saying cyclization leads to decrease in entropy. Delta S of the system is negative in this process. Okay. Where other places we talk about entropy in the whole chemistry syllabus? Remember we talk about entropy in adsorption also. In adsorption, adsorbate gets stuck on the adsorbent. So we say entropy change is negative. Then we talk about entropy change during mixing. Remember liquid solutions? Mixing is always a spontaneous phenomena. Mixing always leads to more kind of interactions, more possible interactions, and therefore mixing ke case mein also entropy change is positive. These small things from here and there in various chapters we should remember very nicely. Chalo, let's take ahead. Now, we move ahead towards defining Gibbs free energy. It is, many people teach that Gibbs free energy ka logic comes from third law. That's incorrect. Gibbs free energy ka logic does not comes from third law. Gibbs free energy ka logic is an extension of second law itself. When we say that del S universe needs to be greater than 0 for a spontaneous process, via lots of mathematics we convert this into del G system should be negative, whose definition we define as del H minus T del S. So second law tells us this, which we simplify into this. G ka definition, G ka logic is not coming from third law. Think, this is how G is defined as absolute level. The moment we differentiate it, we can write it like this. I'm sure you understand I'm keeping temperature out. So whenever I'm using this formula, temperature would be constant. Not just temperature, pressure will also be constant. So del H equal to del H minus T del S mein by default you have two conditions. Pressure should be constant, temperature should be constant. only and only then we can apply this formula. Are you guys with me on this? We cannot blindly keep applying Gibbs free energy change ka formula. Only when pressure and temperature are constant, then we can apply this formula. Now, spontaneity means what? Spontaneity means the change in Gibbs free energy should be negative. Which reactions are spontaneous in nature? Irreversible reactions are spontaneous in nature. Reversible reactions के केस में तो del G is rather 0. Remember, reversible reactions, that means which are at equilibrium. So they cannot move in either direction. If you guys know this, when we talk about an equilibrium reaction and we talk about G, if this is the G of reactant, this is G of product, then at this point you have equilibrium where G is minimum. G is minimum and del G is 0. As you can see, if I try to go from here, it pushes me back. If I go in this direction, it again pushes me back. So equilibrium perspective say del G ka logic is very, very, very important. Whenever we have to relate standard change in Gibbs free energy with non-standard change in Gibbs free energy, this equation is valid. Del G equal to del G naught plus RT ln Q. Q is reaction quotient. This equation is valid always, whether at equilibrium, whether not at equilibrium. When it is at equilibrium, this equation changes to minus RT ln Q and del G was 0, remember? So del G not equal to minus RT ln Q is a special case of a general equation. General equation can be applied at any reaction at any point of time. This is applied only when the system is absolutely at equilibrium. ठीक? Now, this gets covered or gets asked in either electrochemistry or chemical equilibrium. ठीक है, we understand del G, we understand del G naught. We understand naught means steady standard state. Pressure 1 atm, 1 bar, temperature is kept constant, concentrations 1 molar. But what does delta G naught actually depend on? If I have a reaction taking place, then delta R G naught depends on exactly what? So suppose you have a reaction AA plus BB giving CC plus DD, then we can say that del G R naught is equal to sum of G naught of products minus sum of G naught of reactants. Therefore, it will definitely depend on stoichiometric coefficients. Therefore, it will definitely depend on what species the reaction is, and any thermodynamic property we talk about, any thermodynamic property, they all always depend on temperature. Will del R G naught depend on pressure? Suppose there is a reaction, H2 plus O2 gives water. In one case, hydrogen is at 1 atm. Sorry, in one case, hydrogen is at 0.5 atm and in the other case, hydrogen is at 2 atm. Del R G naught will not matter. Del R G naught will be the same because it is calculated when the partial pressures are 1 atm. Right? So del R G naught does not change at all. Is this point very, very, very clear? Very crucial point, guys. Del R G naught does not depend on pressure, does not depend on does not depend on concentrations. Only and only dependence will be on temperature. Please use fourth number option. What? I didn't understand the doubt, Rohit. Fourth writing is not visible. I'm using the fourth number itself. Any which case, I'll improve it in the next time. So guys, we have completed thermodynamics in today's class. I believe we have reached our time. So we'll stop here for the day. We have revised thermodynamics well. Please, please, please ensure that you solve questions in exam. Be cool-headed, be level-headed. write everything that you get and then solve questions. We'll continue the series ahead with more such chapters clubbed together from next time. Thermodynamics is a lengthy one, right? So it always takes long. Thank you so much for joining, guys. I hope you understood the class. Thank you so much, guys. Take care. Bye-bye and best of luck.